Okay, this will be the last video for chapter 16. We're going to cover a few topics, um, and we can talk about Newton's law of thermal thermal exchange. We're going to talk about uh, global warming, the greenhouse effect, and solar power. So let me dismiss my image, and we'll get started. Um, okay. Newton's law of cooling. The rate of cooling is approximately proportional to the temperature difference, delta T, between an object and its surroundings. The rate of cooling is proportional to delta T. In other words, the difference. Let's say we have something at 100 degrees C boiling, and we bring it into a room uh, that's room temperature is about 20 to 25 degrees C. So it's going to have a certain rate of cooling. Now, if we take that same um, 100 degree uh, cup of whatever it is, hot water or tea, and put it in a freezer that's at 0 degrees C, well, it's going to cool much faster. Now, it may not be good for the freezer because you're going to be transferring all that heat energy into the freezer. So you probably wouldn't want to do that. But according to Newton's law of cooling, because the delta T is greater, the rate of cooling will be greater. So a hot apple pie cools more each minute in a freezer than if left on the kitchen table. On a cold day, a warmer house leaks internal energy to the outside quicker than a cooler house does. Okay. Um, it also applies to the rate of warming. Uh, uh, an object that's cooler than its surroundings warms up at a rate proportional to the delta T, the temperature difference. An example is frozen food will warm faster in a warm room than a cold room. Uh, okay. It is commonly thought that a can of beverage will cool faster in the coldest part of a refrigerator. Knowledge of Newton's law of cooling supports this knowledge, shows the knowledge is false, may or may not support this knowledge, may or may not contradict this knowledge. Well, we've just discussed the rate of cooling is dependent on delta T, so it supports this knowledge. When placed in the coldest part of the refrigerator, the delta T, that is the difference in temperature between the can and the surroundings, will be the largest, so it will cool the can fast. I know for a fact that our refrigerator towards the bottom is much colder because sometimes things that are down there they can freeze, even though it's just the refrigerator part. They can get frozen. So I know that the bottom part of the refrigerator, my refrigerator, is colder than the top part. Okay, the greenhouse effect is named for a similar temperature raising effect in forest greenhouses. If you've ever seen a greenhouse, usually just a frame with either some glass or some plastic surrounding it, so that the short wavelength radiation from the sun is transmitted through the glass, but the long wavelength re-radiated energy is not transmitted out through the glass and is trapped inside. That's why they have greenhouses, to protect sensitive plants in the winter. Um, okay, all things radiate at frequencies and therefore wavelengths, because wavelength is related to frequency, determined by the temperature of the emitting object. Things such as glass can be transparent to some wavelengths, but opaque or reflective to others. I know that uh, one of our children was jaundice when she was born, and the doctor said, put her in the sun. Don't put her in the sun behind glass. Take her outside and put her in the sun to help the jaundice, because the glass blocked, I think it was the ultraviolet rays that uh, she needed, and the glass would have blocked those. So glass is indeed um, opaque to some wavelengths. Okay. Excessive warming of a car's interior when the windows are closed on a hot sunny day. We've all living here in South Texas. We've all experienced this. The sun's rays have short wavelengths that readily pass through the car's windows. Absorption of the sun's energy warms the car interior. The car's interior radiates using longer wavelengths that don't pass back through the windows. The car's radiated energy is trapped inside, making the car's interior very warm. I would often say here in Texas, shade beats proximity. I'd rather park far under the shade of a tree than park close to the entrance of a store or something like that in a parking lot. So shade trumps proximity. Okay, global warming. Energy is absorbed from the sun and partly re-radiated by the Earth as longer wavelength terrestrial radiation. So you have solar short waves coming in, and the terrestrial long waves emanating out. But as you can see here, they're trapped by some of the atmosphere. So the terrestrial radiation is absorbed by atmospheric gases and re-emitted as long wavelength terrestrial radiation back to Earth. Re-radiated energy unable to escape, so the warming of the Earth occurs. The long-term effects of climate are of present concern. It is of concern, but I, I think we'll have to adapt as opposed to making it cool down. That's just the nature of it right now. The greenhouse gases that contribute to global warming absorb more visible radiation than infrared, more infrared radiation than visible, visible and infrared radiation about equally, very little radiation of any kind. Well, the greenhouse gases trap more infrared uh, radiation than visible. Um, so uh, I won't go through the explanation of the other choices. We just ignore the other choices. It absorbs more infrared radiation. Okay, more energy from the sun hits Earth in 1 hour than all of the energy consumed by humans in an entire year. That's a lot of energy. Um, and really, it's just a very small portion of the total sun's energy that gets radiated out into space. Um, Now we look at this. Uh, I've entitled this "Solar Power Angle Dependence." This figure is in your book. It wasn't in the PowerPoint, so I added it. You can see that areas A and B are equal in size, but because of the angle of A, I mean, this is just a little demonstration. You can see there's one, two, three, four of these rays that coming from the sun that hit area A, but look at how many hit area B. Is one, two, three, four, five, six. You get more energy. The areas are the same, but because they're hitting almost perpendicularly on B at an angle at A, you get more of them on B. Now, this is my own. If you remember from the first lecture, I believe it was, I showed you that was doing some experiments by measuring the shadow of the mailbox. Well, I've completed over a year of that. You can see from I started sometime in August of 2023, and I've gone all the way to on this graph. I've gone to October of 2024, and I'm still doing it. I'm still collecting data. And what I ended up doing was converting my measurements to angles. And you can see that during the summer, the rays are almost coming straight down. They're not quite at 90, they're at 84 degrees. And you can see that's from about June 7th to I'm going to say about July 7th, somewhere around there. In other words, between June and July, we get the sun's rays coming coming down almost perpendicularly. Now look at the winter. Um, uh, And during the winter solstice, the sun angle is at 38 degrees. So we've got a lot less energy coming in at during the winter than during the summer. And you can see at each equinox, where what happens in around March 20th, March 21st, and I think September, um, uh, some September 20th, 21st, the equinox, the equal day and night. It's at about 60 degrees. So we're getting almost direct, perpendicular sun rays um, at the summer solstice, and in the winter solstice they're at 38 degrees, and we can certainly feel that's why we're so much hotter during in the summer. And I think that that ends the uh, our study on heat transfer, chapter 16 of conceptual physics, and we'll end